record. Whenever the North Pole is allowed to move to the closer side, this is causing the magnet, this is causing this side to experience that my North Pole is getting closer as a more stronger effect compared to the South Pole getting closer. So we are going to have some current regarding this flow. When this magnet keeps on entering and it enters to the North Pole, at the instant when it is exactly entering to the North Pole, you would have the highest rate of cutting and you'll have the brightest amount of glow, which I can show you. Let's say, I'm not going to show the magnetic field right now because just to have a better visibility of this figure. So let's say, if I move the magnet like this, okay, so that way I cannot actually show you. Move the magnet sinusoidally, oscillation speed a bit small, and then I would like to pause it right here. You see, this is the instant, the moment the North Pole is entering to the side, you're going to have the brightest of the glow, because this is, at this point, this coil is experiencing the highest rate of cutting of the magnetic field lines, or most change. Now, as the North Pole is getting into the coil, it is practically getting away from this end. Am I correct?
Yes, sir.
Because it is entering into the coil, so it is practically getting away from the end, and South Pole is slowly approaching this end. So now we are having the two opposing effects: North Pole getting away, South Pole getting closer. So what was happening a bit earlier only the North Pole was getting closer. Now we are having the opposite effect. North Pole is getting farther and South Pole is getting closer, which means now the total change of the magnetic flux cutting, that rate of change cutting is changing direction, because you're having the opposite thing happening. North Pole getting farther away and South Pole getting closer. And this side also is now going to start to experience that North Pole is actually getting closer compared to the earlier case. So if I now allow it to unpause, so as the North Pole gets into it, it is getting away from this pole, and this one is experiencing that a North Pole is approaching it. So now this end would be more susceptible towards the approach of South Pole, this end would be more susceptible towards the approach of the North Pole, and this end would be affected slightly by the leaving of the North Pole. This is why somewhere exactly at the middle, when the coil is exactly at the middle, although it is moving, there is equal amount of effect by both the North Pole and South Pole on both the opposite sides in terms of rate of cutting. So in other words, I can tell you, think about it. Let's say this end is experiencing a North Pole leaving from it. This end is experiencing a North Pole approaching from it. This end is experiencing a South Pole entering into it. This end is experiencing a South Pole approaching towards it. These two effects perfectly counterbalance each other. I'm going to pair them up for your easy understanding. This end is currently exactly at this end. North Pole is currently exactly on the right end. South Pole is exactly at the north end. So if you reverse the sides, let's say this is experiencing North Pole getting away. This is experiencing South Pole approaching. These two EMFs perfectly counterbalance each other. Or I can say that the rate of cutting on both sides of the coil becomes exactly equal and opposite, which gives you a zero resultant EMF. Although it shows a bit of a current over here, but this value of current is exactly zero. I could not pause this animation exactly at the instant of zero. That's why we still have a current, but currently the light is off. It means that currently we don't have any current because the opposite currents have counterbalanced each other. If we allow the magnet to travel further, now what's going to happen? The North Pole is going to come out of this side, and now it's going to start only to get away from the end. For the further part of the motion, the North Pole is getting away. And from this point onwards, the North Pole is only going to keep on going away. But the South Pole is going to have two opposite motion. It is getting away from this end, and it is getting closer to this end. So you're going to have an increase of EMF till this point. Now the magnet has gone a bit further out. So it was the brightest when this South Pole was perfectly aligned with this edge. That is the point you're going to have the maximum amount of difference of cutting. And then as the magnet moves out and decelerates and eventually stops, at this position, we have no current at all, which means the bulb will stop to glow. So what is actually happening? If I start from the beginning, we're going to have one direction of current from here. This is where you have the highest amount of current, biggest difference of rate of flux cutting on the two opposite sides, current reducing, current becoming zero. And current reverses, current becoming zero. So within one going of the North Pole to South Pole, you are having current reversal once. So current reversed once. Then as the North Pole is gonna start going in the opposite direction, we're gonna have a reverse current. Did you see that this arrow just flipped? So as the North Pole, as the magnet starts to enter, the current will flip again. This will become maximum at this position when the pole of the magnet is perfectly lined up with the side of the coil, and this will become zero when the magnet is exactly at the inside of the coil, because now we have equal and opposite cutting on both sides. And now we're gonna have another reversing. So you see this one just reversed right now, and now we're gonna have maximum current right over here when the pole is just leaving from the coil, and as it's gonna get further away, the current is gonna decrease once again and become zero right at this position. Right at this position. So that's how the whole reversing thing is happening. So for one complete oscillation of the magnet, you're having 4 times direction change within this coil if the magnet is allowed to pass through the coil. But if you don't allow the magnet to pass through the coil, let's say if this magnet was only moving on one side of the coil back and forth, for one complete oscillation, you'd only get 2 direction change. So as it was getting closer, you'd get one direction. As it was getting further away, you'd get the opposite direction. But because we are now allowing the magnet to pass through the coil, we're having the change happening from this direction. We're also having the change happening from this direction as well. So we're having a relative change, direction of change for the magnet motion for both sides of the coil. Together, that is making one oscillation of the magnet giving us 4 times direction change, because we are now using both sides of the coil.
Sir, current direction ta ber korbo kiভাবে?
Current direction
reproduce করে?
Yeah, definitely. Right hand grip rule use করে, or you can right hand grip rule. For example, whenever the North Pole is getting closer, this side should be North Pole. If this side has to be North Pole, then it means that the thumb should be aiming towards this thing. It means your current should be happening along this path. So here it is. So North Pole is getting closer. So this end should also become North Pole, which means current flow should happen in this manner. Am I correct?
Sir, ইন্ডাকশনের রুল অনুযায়ী অপোজিট পোল হওয়ার কথা না?
No. Hold up.
The Lenz's law.
Yes, sir. Lenz's law টা most.
ওটাই বলতেছি, Lenz's law basic আইডিয়াটা কি? Magnetic induction will happen in such a way that the region of induction can be opposed. Opposite pole হওয়ার কথা না. Region of induction can be opposed. The North Pole is getting close. You want to oppose it by the coil. So what pole do you require to oppose an incoming North Pole?
North Pole.
Exactly. You are trying to oppose the reason for which the induction is happening. You're not trying to produce the opposite pole, because opposite pole will practically give you attraction. You're not trying to attract, you're trying to oppose. So if it is getting closer, you'll have similar pole. If it is getting further away, you'll have opposite pole. Yes, Sabir bolo. Sabir.
Sir.
Yes.
Sir, আমি flux cutting difference টা বুঝলাম না।
আচ্ছা, flux cutting difference বলতেছি। ফ্লাক্স কাটিং এর ডিফারেন্সটা হচ্ছে ফ্লাক্স কাটিং ডিফারেন্স আবার বলতেছি, ডোন্ট ওয়ারি। বাট বিপ্র, তোমার কোশ্চেন আনসার পাইছো?
পাইছি স্যার।
আচ্ছা, it's not about the opposite pole, it's about opposing the physical reason for which the induction is happening, which warrants or which requires similar pole being produced. আচ্ছা, সাবির, ফ্লাক্স কাটিং এর আইডিয়াটা হচ্ছে we cannot essentially bring about a single magnetic pole close to a coil. If you think about a bar magnet, whenever the North Pole is getting closer, South Pole is also getting closer. That's not incorrect. That's perfectly correct. ঠিক না?
Yes, sir.
But the North Pole is closer in terms of physical distance to the coil compared to the South Pole. So whenever the North Pole is getting closer from one side, the entire effect of the North Pole would be prominent on the entire coil.
Yes, sir.
The effect of the South Pole getting closer will not be prominent.
Yes, sir.
Similarly, when the South Pole would be leaving from the coil, let's say in this case, the South Pole leaving would be the prominent effect, and North Pole effect would not be prominent. So whenever the magnet is outside the coil, whatever the end of the pole of the magnet is closer to the coil will dictate the behavior of the coil.
Yes, sir.
And whenever the magnet is allowed to enter into the coil, this is actually pretty unique animation. I haven't seen this animation anywhere else. Whenever the magnet is allowed to enter into the coil, you have a flip or reversal of preference. What do I mean by the reversal of preference? For example, in this case, the South Pole is entering from the right end. So the entire coil is currently under the effect of South Pole getting closer. But what you have to understand, the rate of cutting that you have from the South Pole side of the magnet onto the coil, that is a much stronger effect compared to the rate of the compared to this North Pole end cutting, because then this North Pole also have field lengths over here as well.
The North Pole কে এখন কাট হইতেছে
Both
এখন
side,
যে
yes, yes.
orientation থাকতেছে
I mean,
কিন্তু
the field lines actually extend from the North Pole all the way to the South Pole, right? The field lines do not only belong to the South Pole or only belong to the North Pole. They belong to both of the poles, because these are continuous lines coming out of the North Pole getting into the South Pole. Interesting bit is that the concentration of the field lines coming out of the South Pole is more close to the South Pole, and on the North Pole side it is more over here. So the rate of cutting produced by the South Pole side field lines is more stronger compared to the rate of field lines coming out from the North Pole side. Now, if you want the North Pole field lines cut kortechi na, well, field lines belong to both of them. That's why I say
The question is which one is closer.
the question exactly that's the primary factor by which the behavior will be affected. So when the magnet is outside, you can only use one pole to define their behavior. But when the magnet is allowed to get in, now this coil is affected by both of these effectors. You have to understand that this side is experiencing South Pole getting closer, this side is experiencing North Pole getting closer. Am I correct?
Yes, sir.
yes
Yes,
sir
sir.
So shouldn't they produce opposite voltage?
Yes,
Yes,
sir.
sir.
Do we volt direction of voltage produce?
They will produce opposite voltage, and they produce exactly opposite voltage when the magnet is perfectly inside. As long as the magnet is not perfectly inside, there is a difference of voltage produced. So let's say when the maybe let's say, oh, let me just, there's no way I can revert this, so I'll just wait for one full cycle. Okay. So what I want you to understand, let's say in this case, South Pole is about to enter. It is producing, let's say, some voltage into the whole coil. Let's say this South Pole is producing a total of, let's say, 10 volt plus 10 volt over here. This North Pole is producing, let's say, minus 1 volt over here on the whole coil, because both of them are approaching to the coil. So the total output of this coil will be plus 9 volt. South Pole is producing plus 10 volt of its own effect. North Pole is producing minus 1 volt by its own effect. Resultant is plus 9. If you allow the magnet to move in, now let's say the South Pole is getting closer to the left end and North Pole is getting closer to the right end. They are now both approaching towards two opposite sides of the poles. So there will be pretty much opposite EMF produced. So for example, let's say in this case, we still have some EMF produced. So let's say that this South Pole is producing a total of, let's say, plus 7 volt on this coil, and North Pole is producing maybe, let's say, plus 3 volt on this coil, minus 3 volt on this coil. So you have a total of some addition, plus 7, minus 3, you get a total of 4 volt. So your total output is reducing. When the magnet is pretty much at the center of the coil, these two things perfectly balance each other. Let's say now the South Pole is producing a plus 5, North Pole is also producing a plus 5. So they cancel us out each other's effect, and the total EMF produced in the coil becomes practically zero. So there is no current and the bulb is no longer glowing. This is the part that I wanted to discuss for the response of your question. বুঝা গেছে কি বলছি?
Yes, sir. এগুলা কি O level এ আসে?
না।
Never seen in question.
না,
পড়ার সময় দেখি।
তোমাদের O levels এ allow the coil allowed to move through the magnet, the magnet allowed to move through the coil. This scenario is actually quite scarce in terms of question content for your O level. I have not seen it so far. So far in your O level syllabus, what I have seen, you are only asked about question that when the magnet is allowed to move closer to the coil from one side. The magnet allowed to move through the coil is actually very, very, very rare. But then again, I would say, if you ask me that do you need to know this part of the discussion that I just discussed with you can belong to the shady or dotted part of the syllabus, that it is logically understandable by the kids from their pre-knowledge, but it was not explicitly mentioned in this question. So if the examiner set questions about this part, You cannot say no to this. Then again, they are not supposed to set questions about this part, but they can. That's the difficulty.
Yes, sir.
Achha, sir. Can I make a concept clear, sir?
But
That is,
go ahead.
sir,
Oh,
as soon as we are entering a North Pole, the electrons are pushing, due to this positive charge, I mean, the electrons are pushing themselves towards the, this is the right side of the coil. And when they are leaving, I mean, when the North Pole is leaving, they are, I mean, again, pulling themselves back.
okay.
Can you see that?
Yes, you can say that. Opposite movement of the coil on the same side of the opposite movement of the magnetic pole of a single magnetic pole for opposite sides of the coil will cause the electrons to move in opposite direction. Yes.
And sir, because all the electrons try to move over here, we have a positive uh, positive end at the left side, and that's why the North Pole is repelled when it enters, and when it tries to exit, the electrons try to get back to their position, so it is attracted.
Beautiful. Perfect.
Oh yes, thank you, sir.
Sure. So this is one of the mind-blowing simulations that this website has. And then if you ask me for more important, interesting parts, I'm going to share this website with you in a moment. I'm just trying to show you what this thing has. This is just amazing. Over here, we can design a circuit. Let's say this one.
Sir, what is more mind blowing is your live class, sir.
স্যার এটা কি অনলাইনে ফ্রি?
Yeah, I'm making the circuit here. So let's say I have added two resistors. I can actually label this resistor as 10 ohm. I couldn't figure out how could I label them. Do I drag it or oh no, I don't need this. How can I get rid of that? Never mind. This is R1. Let's say R1 is 10 ohm. Okay. I actually couldn't figure out how to do this thing, but what I can do, for, what I'm sure that this thing can be done. I can drag multiple components over here in different orientation, and you can actually place them as different parts. These are bulbs, switches, capacitors, batteries, resistors, ammeters, wires, and you can give arrows, individual arrows. And these rectangular boxes, I believe they appear for other parts. And you can make an effective circuit, and eventually you can make questions out of this circuit for the students to work with them. There are some amazing other stuffs that I would like to show you, that the graphs গুলো যেন কই ছিল এই যে এখানে so let's say we have a velocity time graph for an object like that. So what would this cause the acceleration time graph to appear to be as, or what would this cause the position versus time graph to appear to be as? So this actually goes on to show some value representation. So like that. If I make it a uniform velocity, you're gonna have a straight line starting from this. So you can see over here that this is uniform velocity. So you have no acceleration, zero acceleration. It's a straight line. Then if I make it uniform increased velocity, you're having a increasing gradient, and where the acceleration graph is perfectly a horizontal line. We are having a bit of a difference because I could not place this point properly. Well, now it's a constant acceleration. If you have a variable acceleration, for example, let's say if this thing is over here and this thing is over here, you have a difference in value. But what is interesting for you to understand, you can see that throughout this graph, we have positive velocity because this entire graph is belonging on the positive y-axis. So you are never having the object going in the reverse direction. But if you bring this point down, this one shows you what? That for this part we have a positive velocity, and for this part the object has a negative velocity. It means the object is going down, going backwards. So here you can see that from this part up to this much part, I mean up to this much point of time, the object is getting the farthest away from the position because this is for this triangle represents a positive velocity. This is increasing velocity, this is decreasing velocity. So you have increasing gradient, let's say up to this point, and then you have decreasing gradient up to this point, representing a negative velocity. And then the object is moving back towards the original position because this is negative velocity. It means the object should have moved in the reverse direction. So for this part, from here up to this much part, the object was moving to the right, let's say, and then it moved a bit to the left because it is getting closer to the original position. And then the object is once again going ahead. But if I make this whole thing go down, let's say, if I make a negative velocity graph altogether, this is the situation. Now here I have I've tried to show you a graph which shows you that the object started at some certain point and eventually after the whole time t, it came back to the same point, which means the total area that you can calculate out of this triangle and the total area that you can, I mean this triangle, and then the total area that you can calculate for this triangle, they'll be exactly equal. So object যতটুকু further move করছিল, which is equal to this much part, ততটুকুই আবার সে উল্টা দিকে move করে চলে আসছে. So first it moved to the left. I'm using the term left because this is the negative displacement, and then it moved to the right by the same amount, ultimately giving us the exact same value. And we have two different values of acceleration because this line is a straight line. So here, this is a conversion from velocity time graph to position and acceleration time graph, where I can make a lot of different questions for you. That
acceleration time graph manipulate করে বাকি দুই গ্রাফ পারা যায়?
সেটাও possible, but it would require much.
So acceleration graph to behavior বুঝতেছি না.
This is the other animation that Sabit just asked me, that in this case, you can control the acceleration time graph and you can have different values of the velocity time graph, which actually, in this case, you can actually control all of them individually. So you can control the starting velocity, and depending on the starting velocity, you can have different shapes of graphs. And depending upon that, you can have different values of acceleration time graphs. We don't have any scale over here, but you could give any scale that you want. And that pretty much works for your requirements. So if you start the object from 0, this part shows negative acceleration, so you have a negative gradient. Then it shows a very large positive acceleration, so you have a positive gradient. Then it shows even higher positive gradient because this is the, you have to understand, a graphic gradient হচ্ছে এখানে plot করা, right? A graphic gradient এখানে plot করা, a graphic gradient এখানে plot করা. So from this part to this part, the gradient should decrease. You see, this is starting with horizontal, 0 velocity, and you have a decreasing gradient up till this much. You are having a negative velocity. Then from here to here, the gradient is increasing because the line is becoming flatter. So you are having a increasing gradient for the DT graph, where you have constant positive velocity or increasing velocity, and then it has constant velocity. Sorry, uniform acceleration. So you have an increase from here to here, and then this segment is a perfect straight line. So because you have constant velocity over here. So each of these segments particularly represent that how one type of graph can be converted to the other type of graph, which makes it very easy and visual to understand. I find this website amazing.
Sir,
বলো।
So acceleration versus time কি আমাদের আছে? না আমরা করতে হয়?
Not defined in the syllabus. This is a friction case which you might not have for your stuff, and then I show you the lenses part over here. And oh, I should show you the eye problem. Where is that? Optics of the human eye. So this is the opticals for the human eye. So you have normal vision. So normal vision is whenever object is here. So I should don't move these things. So focus is, let's say, over here. So if we make the object far away, I mean, this is what is happening. I mean, you bring the object farther, the cross point becomes closer. So I cannot get this out. What is happening? আচ্ছা এখন ঠিক আছে। Oops, that's good. দাঁড়াও আমি ঠিক করতেছি, কি কি বলতে যাচ্ছি এটা ঠিক করতেছি। ওকে, মনে করো এটা হচ্ছে আমাদের রেগুলার আই এর নরমাল ডিসটেন্স। সো লেটস সে দিস ইজ দ্য ফোকাস পয়েন্ট। সো a regular eye would see an object over here. So normally if we take the object further away, the cross point comes closer, and if we take the object further close, the cross point becomes less. So what does the normal eye do is it changes the focus point or the thickness of the lens, that whenever the object goes further away, it makes the lens thinner so that the focus point gets back to the original position. And if the object is placed closer, it makes the lens thicker so that once again we have the rays merging at the same position. That's how the normal eye works. It changes the focal length accordingly so that it can get the crossing of the light rays easily on the retina. You don't have any other anywhere else. What happens to the nearsighted eye is that it sees objects, far objects pretty clearly. Let's say it will be able to see sorry, nearsighted means it can see the it can see the close objects pretty clearly. For example, let's say when the object is over here, it can see it pretty clearly like that. It's over here, it can still manage it, but beyond a certain point, it cannot manage it anymore. For example, when the object is pretty far away, then it cannot manage to do this thing. It is limited over here. So it is the maximum focus at this one it can do. So if the objects are pretty farther away, this thing comes even closer and closer and closer. So object position further, and where is the correction? Where is the correction? For one position, I did get the correction. Okay, fine. This is the problem for the nearsighted eye, that the object, when the object is really far away, then the rays actually fall in front of the retina. If we want to correct the nearsightedness, we just simply place a concave lens over here so that the rays are a bit more spaced apart, and then eventually they meet on the retina properly. So that's the correction. And then I can go for the far-sighted as well. Bring the object close. And then if you want to correct the far-sighted lens, that's essentially what we do. So we place a lens over here, which makes the rays more convergent and the far-sightedness is clear. And you can also apply the eye anatomy if you want. This is not in physics, but this is in biology, but you get the point how the whole eye thing works. তোমরা কেউ কি বিরক্ত হইতেছো? You might, but
No, sir.
I actually personally find this amazing. And then for fun stuff, I find this one very amazing.
Sir, how do you do this, sir?
They did it by mathematical modeling.
I mean, how would you do it?
I can never juggle 13 balls. I can rarely juggle 3 balls.
Sir, isn't there any balls? Oh no, 13 balls. Sir, you can increase the speed if you want.
Yeah.
Now this looks far more realistic, sir.
This is much more difficult if you ask me. All right, let's go for electronics.
Sir, what do you mean by electronics?
Um, what I'm about to discuss, that's the electronics. ইলেকট্রনিক্স চ্যাপ্টার আমাদের কি কি আছে? আগে আমি তোমাদের সিলেবাস দেখাই, তারপর তোমাকে একটা একটা করে জিনিস পড়াচ্ছি। না ভাই, তোমার পরীক্ষা যাবে 2021-এ।
স্যার
ইয়েস, মানে
আচ্ছা স্যার, আমি না লাস্ট ক্লাসে প্রেজেন্ট ছিলাম না, আপনি কি ট্রানজিস্টার করেছিলেন লাস্ট ক্লাসে?
না, ট্রানজিস্টার এখন পড়াবো, লাস্ট বিভব পড়াইছি।
আচ্ছা স্যার, স্যার এটা রেকর্ডিং আছে?
হ্যাঁ, লাস্ট রেকর্ডিং আছে, মনে হয় আপলোড করা হয় নাই, বাট আই হ্যাভ দ্যাট।
ওকে স্যার, থ্যাংক ইউ।
Okay, this is the introductory electronics. Have a look. First, we have to know thermal emission of a cathode rays, uses of an oscilloscope, action and use of circuit components. একটা করে পড়ে যাও। State that electrons are emitted by hot metal filament. State. This is the basic working principle for the CRO. CRO we have covered. এখানকার most of the part হচ্ছে CRO পর্যন্ত। একটা করে পড়ো। State the electrons are emitted by hot metal filament. We know about that. You can state that. Explain that to cause the continuous flow of emitted electrons, a high positive potential and a very low gas pressure is required. It is obvious because using the high positive potential, you're going to attract those electrons towards the anode, and you need very low pressure gas so that the electrons do not collide with the air particles and get absorbed. Describe the diffusion of an electron beam by electric fields and magnetic fields. We have discussed about these parts in our relevant chapters. State the flow of electron or electron current from negative to positive and is in the opposite direction of conventional current. Acha, এটা তো historical mistake, we know about this as well. Describe the use of an oscilloscope to display waveforms and measure PDs and short intervals of time. The structure of the oscilloscope is not required. Structure of the oscilloscope is not required means that you do not have to know the exact inside details for how an oscilloscope works to its very minute level. But you have to know that in the individual three segments, that you have a electron gun part, you have a deflecting plate part, then you have a fluorescent screen part. You have to know about those three parts and how these three parts can work together to give us the display information, whether it's a sine curve or it's a flat line or it's a single dot, irrespective. But you don't have to know exactly what type of circuits and what type of logics actually, or what type of circuit components actually make the whole thing work. You don't have to know that very minute detail, but you have to know those three segments about them. And then it says that describe the use of an oscilloscope to display waveforms and to measure periods and short intervals of time. This is basically how we can extract information out of the cathode oscilloscope graph. For example, if you are given a graph, you should be able to read from that graph that what is the supply voltage is, what is the time period of that voltage if it's an AC supply, etc. That's one way of question. The other question is that if you are given a set of information and given a blank piece of graph, you should be logically able to draw that graph, which both of us we have covered in the CRO part lecture. Question number F says, bullet number F, explain how the values of the resistors are chosen according to the color code and why widely different values are needed in different types of circuit. Well, you know how to do the color code. This is the first number, which is the 10th digit, second number color, which is the unit digit, into 10 to the power C, which is the third digit. And sometimes you have a 4-digit which goes for the tolerance. Tolerance is not required for you, but that's the way it works, which we covered in the electricity chapter. G number says, discuss the need to choose components with suitable power ratings. Suitable power ratings means that whenever you're connecting some device with a supply voltage, their power rating should be designed. I mean, they should be designed in a way that they can handle that device, handle that power supply. For example, uh, let me put up a simple example. Power rating essentially does not mean that what its exact power is. Power rating essentially means that what its rated voltage is and what voltage you are connecting it to. For example, if you take any regular electric component, you would always see some labeling on its side. For example, it might say that 2.2 ampere, 220 volt. It means that you're supposed to use it in a 220 volt supply, and in that case, it's gonna pull, let's say, 2 ampere or something like that. Now, it is important to take into consideration the power rating, because if you do not take into consideration for the power rating, uh, components will burn, which is a pretty common problem for typical DC circuit relevant experiments that we teach the kids in our laboratory. Try to understand, the electrical power is given by P equals to I square R. So the primary factor that controls the current, more strongly controls the power or heating effect of a resistor is the current. So if you have a large current, you're gonna have a very high heating effect, and vice versa. The only logical way, and there are multiple different ways actually, but not, I shouldn't use the term only, my bad. One practical way to reduce the current or limit the current within a resistor is to have its resistance increased. So if you want to lessen or lower the amount of heat generated by resistor in a circuit, you preferably should choose a resistor that has a high resistance. A high resistance value would essentially give you a smaller current. That way the heating effect would be limited and you don't have to bother much about that thing, which actually is a good enough thing. However, if you don't want to, if for some requirements, you have to use a small value of resistor. For example, let's say for some experiment, if you have to use a resistance within the range of, let's say, 12 to 15 ohms, then essentially the current value would be extremely large to the circuit. That high amount of current can heat up your resistor too fast, and it can burn up your resistor. That's a very important consideration. Now, you have to understand a couple of things. How does any electrical component burn? How does anything burn? How does anything burn? To give you to first get the concept of burn, you have to think about the process of heat transfer. There was one of this experiment in your heat chapter, actually in heat transfer process, that if we had a cylindrical object made from two materials, one side was made with copper, the other side was made with wood. Do any of you remember that thing?
No, sir.
Yes, sir, or no, sir? There was a
Sir.
there was a two material cylindrical object which was being heated, which was given in your heat transfer chapter. One side of the cylinder was made up from metal, the other side was made up from wood. There was an example like that. Let me find this for you. Hold up. I'm going.
Sir, রডের এক্সপেরিমেন্ট ছিল স্যার
স্যার ওয়্যাক্সেরটা কতটুক ওয়্যাক্স
মেল্ট করে
না, wax না, paper charred হওয়ার একটা experiment ছিল.
না সেটা জানি না
You would hold this onto the paper and on a flame, on মানে quite high on the flame. দাঁড়াও, এখানে পাইতেছি না, এটা হয়তো তাহলে কোশ্চেন পেপার কোথাও থাকতে পারে। আচ্ছা, let me find out this figure from the net. Exactly, I see. So I'm talking about this part. So this is one of the experiment that I need you to think, that we have made a composite object, maybe by gluing them inside in between or somehow joining them. So the right side is made up of wood and the left side is made up of copper. Copper being a metal, it has a very high heat conductivity. Wood is non-metal, so it cannot conduct heat very fast. So this is the actual example that we have in this case we have a metal and we have wood on the other side. So what we're gonna do, we're gonna apply low heat to both of these parts. So this is the heat we're applying it. What we're gonna see that the part of the paper which is on the wood side is gonna start charring. Charring means it's not gonna essentially go up in flames, but it's gonna start becoming blackened. That it is actually becoming the thermal dissociation into carbon. And this part is gonna burn out, and the wood is also gonna have some burnout, something like this. You can see in this figure as well, something like this. However, the part that is on top of the copper part would not burn. Now, this does not mean that the copper part paper was unburnable, that something happened to the paper. No, the idea is very simple. Heat was being transferred to the paper on both sides at equal rate. This part of the paper being in contact with the copper could get rid of that supplied heat to the copper piece, and copper could take it very readily because copper is a good conductor of it. Whereas this wooden piece could not take that heat very rapidly because wood is a poor conductor of heat, which means the amount of heat that was supplied to this part of the paper got accumulated over time. The amount of heat that was supplied to this part of the paper got dissipated into the copper rod over time. So this part could get rid of the heat, this part could not get rid of the heat. So this part's temperature got higher, but this part's temperature did not continuously get higher. It got higher a little bit, but from a certain point, it will not go any higher because at that point, it will be continuously taking heat from the flame and giving the equal amount of heat to the copper rod at the same time. So it would be slightly higher temperature than room temperature, obviously, but its temperature would not keep on rising continuously. Whereas this part of the paper, if this one's temperature is rising continuously, what this will do, this part will eventually reach to the temperature of chemical dissociation or burning temperature. This part of the paper is not reaching to the burning temperature, so this part of the paper is remaining in paper shape. It is not charring up, it is not taking a flame, it is not burning, but this part will burn. The whole idea is about heat dissipation. So why am I bringing up this example? You have to understand that in any case, any object will burn if its rate of heat production or rate of heat taking is higher than its rate of heat dissipation. একটা অবজেক্ট যে রেটে হিট অ্যাবজর্ব করতেছে যদি সে তার থেকে কম রেটে হিট ডিসিপেট করতে পারে তাহলে ওভার দ্য টাইম ওই রিমেনিং অ্যামাউন্ট অফ হিট তার মধ্যে আস্তে আস্তে জমা হতে থাকবে। That's the basic part, simple math. So if an object is being here at let's say 100 watt, that is 100 joule per second, it can only dissipate let's say 80 watt, which means 80 joules per second. Then every second 20 joule of energy would get stored within the object because it cannot dissipate that. Every second is going to have a storage of 20 joule, which means over the time it's going to store up more and more and bigger amount of energy, and eventually it will reach a temperature where it will catch a fire, or it will burn itself, it will melt itself, or it will dissociate itself, or it will do the reaction with the atmospheric oxygen. Something will happen. That's basically burning. So what I want you to understand that the mechanism for anything to burn is that we have a lower rate of heat dissipation and an increased rate of heat absorption or heat production. This is the reason in many cases hot objects have metal fins. We have metal fins so that we have increased surface area for the air molecules to heat it, and as a result the heat transfer rate can be increased. And to further increase it, if only metal fins are not good enough, we also apply fan to those metal fins so that there is continuous flow of cold air, which increases the heat transfer rate. And those metal fins are also in most cases painted black so that they have a bigger amount of thermal radiation, because black objects are good radiator objects. In some cases they might not be painted black because whenever their bare metal surface is exposed to the fan, because having a coating of painting might apply some insulation. Not having that coat of painting would expose the bare metal. So you have to consider that which one is more beneficial for your purpose. I mean, having it colored, painted, does it give you more increased radiation, increased giving up of heat, or keeping the metal piece bare open with the in front of the airflow, that gives you a better heat dissipation. So comparatively যেটা better হয়, that is the typical design choice, but it can be both. If we paint it black, the reason is we want to have black objects radiating more rate of heat. If it is not painted black, the reason is we want to have the bare metal bare metal surface or exposed to the incoming airflow so that the atmospheric molecules can take a heat much too easily. So there is reason for both of them. So this is a question of uh, optimization or sweet spot, finding the sweet spot in the experiment. So when the point where I actually differ from this point discussion is that this is the point that this is the need to choose the components with suitable power ratings. This means that we have to first of all apply connect equipments with the exact rated voltage value labeled on them in the appropriate power supply. So 220 volt means you have to apply 220 volt supply. If it is less than that, you have to provide a lesser voltage than that. Around the entire wall, we have usually two standards. We have 110 to 120 volt. That's one type of standard, and or we have 220 or 240 volt. That's another type of standard. Typically, let's say 5 to 10 years earlier, we had all of these equipments which are completely different from each other. So if they are not matching up with the rated voltage, you'd just have to buy a new one that would match the rated voltage. But currently, especially the mobile chargers, they are all designed in such a way that they will all be capable to work in both the ranges, because people travel a lot. They use the same mobile charger. Let's say one person is today is in London, the next day they are in America. If they want to use the same charger, and they have to continuously remember that and flip their chargers back and forth for the two different voltage rating, which is difficult. So currently they have somehow designed a smarter way so that the equipments can manage to charge or operate in both of the voltage rating environments. So that's the idea about choosing the proper power rating. And the other thing that is important is that we should not choose any equipment that does not have enough ability to dissipate power so that it does heat up too fast and eventually burn. For example, in the laboratory, I actually have two sizes of 10 ohm resistor. Let me show you this thing. I might be able to show you this thing. Take a look. All of these three resistors are 10 ohm, but they have different size. The lowest, smallest one, which is the typical one that that we use in our lab, this has a power rating of 0.25 watt, which means it can manage to dissipate up to 0.25 watt only. If the power produced within this 10 ohm resistor is more than 0.25 watt, it will start to heat up. It will start to store heat up, and eventually it will burn. The green one has a power rating of 5 watt, but that rectangular block, still 10 ohm resistance, it has a power rating of 11 watt that can take up to 11 watt of power. So that's the difference, that we have to choose equipments for our applicable applications with appropriate power rating so that we know that while functioning, it will not burn out. And we have to plan it ahead. That's the meaning of this phrase. এই ডিসকাশনটা বুঝা গেছে কিনা?
Yes, sir.
বলবান, everyone else.
Sir, basically the power rating given shows up till what power rating the component can dissipate the heat fast enough, right?
Yes, essentially, or it will be functional enough.
Otherwise the heat will accumulate and after some time it will burn.
Yes. So that's that. So if we go for the next one, describe the action of a thermistor and light dependent resistors and explain their use as input sensors. Thermistors will be assumed to be of negative temperature coefficient type. আচ্ছা, এই জিনিসটা মানে কি? ইনপুট সেন্সরস এর জিনিসটা মানে কি? এই জিনিসটা আমি তোমার বুঝাবো তোমাদেরকে, যে থার্মিস্টরস এবং এলডিআর ইউজ করে আমরা কিভাবে একটা সার্টেন ডিভাইসকে সেন্সর হিসেবে ইউজ করতে পারি। So let me discuss this part with you in detail. These two devices are usually used as an input device along with a transistor, typically. So I'm going to go through the entire list, then I'm going to pick up the points that I would like to see. But let me go through the entire list first. So then it says describe the action of a variable potential divider. So how can we use a variable potential or a potentiometer? You have know how to use a variable resistor. So it's just the sliding contact position that can give us any fraction of the supply voltage by in terms of the ratio of the resistance, which can be also said to be the ratio of the length of the resistance wire. That also works. Next is that describe the action of a diode in passing current only in one direction only. So describe the action of a diode. This part would require detailed discussion, so I'm going to go through this part as well. Describe the action of a light emitting diode in passing current in one direction only and emitting light. আচ্ছা, এখানে একটা জিনিস তোমাদেরকে বলি, describe the action of this thing. Describing the action means that you are expected to be able to say in detail what happens when something is changed. You don't necessarily have to explain what is the internal working of the whole thing or which that thing happens. So you're not trying to explain the behavior of that equipment. You're trying to describe the behavior of the equipment, which means এটা হলে এটা হবে, এটা ইনপুট হলে এটা আউটপুট হবে, এটা চেঞ্জ হলে এটা এইভাবে চেঞ্জ হবে. You are supposed to explain that. So what for what? You're not trying to explain what for why. So get the difference. You're not, it is not included in your syllabus to able to discuss that what changes happen or inside the equipment, or what is the function, or what is the reason for which this device functions in the manner that it is mentioned to function. You're not going to be asked for that reason. You don't have to explain its working. You have to just describe its working, that what type of change of action that we have from these things. Then it says that describe and explain the actions of relays in switching circuits, which you have seen for relay circuit, how they work. That we turn up the low voltage circuit to turn up a high voltage circuit for safety and stuff. We have discussed this in our electricity chapter as well. Describe and explain the circuits operating as light sensitive switches and temperature operated alarms using a relay or other circuits. Don't worry about that. Here comes electronic systems and then data systems. So let's have a look at this table. We should be able to describe the bipolar non-infinite operators with the circuits. Okay. State in words and in future foundation point logic gates. তোমাদের logic gates পড়াইছি না?
না স্যার।
No, sir. No, sir.
আচ্ছা ঠিক আছে, পড়াবো, don't worry. So it is simple. Why do I feel like this logic gates পড়াইছি? My brain tricking me.
The majority of that portion is from computer science, right?
তোমাদের ব্ল্যাঙ্ক গ্রাফে গ্রাফ I showed you a video of this one, did I not? For the ring. Did I show you a video for this thing? Ultrasound cleaning of a ring. Maybe I did. Maybe you are not gonna tell me. I cannot apparently find any of the questions where they have put up a electronics question. I don't know why. Is it only available in the summer session? I will go for the summer sections. Will I be able to find that? Ah. This is a very nice Formula One car.
So logic gets another worksheet नहीं.
I don't think so. দেখতেছো তো লজিক এসে কোশ্চেন তোমাদের সে সেট করে না অবশ্যই বানাবো কি দিয়া I've been looking for so long to find out one question to set you an example. Can't find it. This is the nice thing. This is a nice figure. Spray painting whole thing. You guys know what is happening here, right?
Yes, sir.
Yes, sir.
It's nice.
Yes, sir.
Alpha particle, gamma particle. দূর খুঁজতে ইচ্ছা করতেছে না লাস্ট একটা জিনিস দেখি যদি কভার ভালো হয় তাহলে হয়তো এখানে পাবো না নাই বাদ পরে দেখাবো তোমাদেরকে কোশ্চেনের মাঝখানে অর দিয়ে দেওয়া থাকে that you will know that which part that you that is optional না নাই আচ্ছা পরে কোনো সময় খুঁজে বের করে দেখাবো না সো আচ্ছা আমি তো সবই অফ করে দিলাম তো ঠিক হলো না সব অন করতেছি আচ্ছা করি So let's go for the bullets that I told you that I was going to show you. First of all, that how can we discuss this is the action of thermistors and light dependent resistors, and I assume they're used as input sensors. So how can we use them as input sensors? So let me show you an example for one of the stuffs, which I might have a compilation for. That's the 2 questions. Oh no, 3 questions. There are 3 questions here. This is nice. আচ্ছা এই কোশ্চেনের ওয়ার্কিংটা তোমাদেরকে দেখাই ফর এক্সাম্পল this question tells us that figure 8.1 shows a transistor used in the circuit of a simple moisture detector. So this is a circuit. We have a water within the beaker. We have 2 metal contacts. We have a lamp. We have a battery. Describe what happens when the water level in the beaker reaches the metal contacts. Achha. The way transistor works is that this part which comes out from the flat end middle point is called the base connection. The one that enters is usually called the emitter. The one that comes out is usually called the collector. So this is the main pathway of the current. How much should this pathway of the current be depends upon how much current flow is available through this path. So this is sort of like the controller in a certain proportion for how much current flow can happen through here. So let's say if this transistor is designed for, let's say, for a factor of 100, it means logically speaking, just mathematically speaking, if the current in the base connection is 1 ampere, you can achieve 100 ampere current through this one, but it's pretty really high value. So if I calculate this, for example, if you have 0.001 ampere over here, you can have 0.1 ampere through here. So whatever the current flow that you're going to have in the base wire, you're going to have 100 times the current over here. So a transistor can have a factor of 100, it can have a factor of 2000, you can have a factor of 1 million. We can design the thermistor to have that factor in certain different fractions depending upon the use that we're going to do it for. So how does this whole circuit is going to work? Now what you have to see that this battery is providing a simultaneous supply for this part of the circuit. So take a look at the way let me just আচ্ছা এখান থেকে এডিট করলে তো এডিট হবে না এখান থেকে এডিট করে so yeah better this circuit is currently providing a possible path for the current flow that can work in 2 different ways. So current flow can happen, come out from here, go up, and eventually it can flow through the lamp. Maybe it will flow through this pathway and usually come back to the negative end. This is one pathway of the battery. Current can also go from the positive end out, go straight way, and usually come to the metal end. And maybe if this water surface touches the two metal contacts, current can flow through that water and eventually fill up the circuit, and current can flow through this pathway back, and eventually from here, once it reaches here, it's not going to go up because up is the high voltage side, the bottom is the low voltage side. So current is simply going to enter through here and it's going to simply flow like this. So this battery,
Why doesn't it go the high voltage side?
because current always flows from high voltage to low voltage.
Yes, sir.
So whenever the current reaches up over here, if you try to understand, this end represents the negative side of the battery. This end represents a fraction of the positive side of the battery. I'm using the word fraction because the lamp will eat up some voltage, but still this will be somewhat positive, but this will be negative. So whenever the conventional current reaches this point, it will naturally prefer to go to the low voltage side, not to the high voltage side. So, yes, sir. Please.
কনভেকশনাল যে কারেন্ট ডিরেকশনটা আরেকবার দেখাইতে পারবেন এই যে ট্রানজিস্টরের জন্য? জি স্যার।
Okay. So এখানে আমাদের কোশ্চেন যেটা বলছে, the question says that describe what happens when the water level in the beaker reaches the metal contact. So what's gonna happen? So acha, before I get into this question, the point that I was trying to highlight সেটা হচ্ছে যে whether the current should flow through this path is dependent on whether any current flows through here or not. This current of this pathway control works like a control switch for how much current can flow through this pathway. If there is no current flowing through this pathway, no current should flow through this pathway as well. If there is some amount of current, this should be opened up in a certain proportion, and that proportion value can be designed while manufacturing that transistor. You can do that. Now, important factor that I want all of you to understand is that whenever the water level rises up and touches the metal contacts, current can flow through the base connection of the transistor, which opens up the pathway for the lamp current to flow through itself. So in that case, the current will flow through the water, leading to a value of the base current. This is the base connection. So let me write that. This is the base connection. And this will open up the current flow path through the lamp, and the lamp will glow. And the lamp will keep glowing as long as the water level is touching these two metal contacts, which means they are conducting current. Whenever the water level will fall down once again, this current flow will stop, and this current flow will stop immediately. So this whole circuit, this lamp, can work as a detector for how much this water level is. If this water level is not touching the metal contacts, the lamp will not glow. If this water level is touching these metal contacts, the lamp will glow. That's the way it is. That's the way it is. So if we have a look at the solution for this question, let's have a look at what the examiners have given us. Just a second to wait, Koro. This is a 3-mark question. So let's have a look at the mark scheme, and then I'll take your questions.
So, sir, from one side,
just wait a bit. Let me look at the mark scheme a little bit, then I'll take your questions. একটু wait করো. Water converts to completes the LH circuit or left-hand circuit, small current into the base of the transistor, or VB is bigger than 0.6 volt. This part, এটা কোত্থেকে আনছে তারা? আল্লাহ জানে. This part is not relevant to the question, but they have given it in the masking. Switches the transistor on or large current from collector to emitter or in lamp. So collector to emitter means what they are proposing, that the entry point is the collection point. So this is the C point of the thing, and this is the emitter is the output point, which I told you earlier. You don't have to label this. I'm just labeling this to make sense to you for the answer. And the lamp switches on. Lamp switches on. Alone 0. Achha, if someone only mentions lamp switches on, this will not give them any mark. So if someone just write the lamp switches on without writing any of these parts, they are gonna get 0. They have to give this series of reasoning. So first of all, the water conducts and completes the base current circuit, which is this one. This opens up the collector to base current. This allows a large current to flow through the lamp, and the lamp glows up. What is the third point? Switches a transistor on, or large current flows through this thing. Acha. Water conducts so check mark. Base current exists at a check mark, and the transistor gets open, or the light glows up. Current happens through the lamp is a third mark. This is the distribution. হ্যাঁ বলো কি কোশ্চেন বলতেছিলা?
স্যার এটা কিভাবে ওয়ার্ক করে স্যার, এখন আমার বুঝতে সমস্যা হচ্ছে স্যার। এটার ওয়ার্কিংটা এটার।
Yes, sir.
Okay.
স্যার মাইকিংটা আবার একটু বলবেন?
Acha, sir, one more thing, sir. Why would current coming from both sides, I mean, provide a large current? I mean, from one side it would also be enough, right, sir?
আচ্ছা, আর কিছু? Any other
কিভাবে
question?
a small current translates into a big current?
Okay.